For years, the transformer architecture and its self-attention mechanism have reigned supreme in deep learning. However, as sequence lengths scale, self-attention's quadratic computational complexity presents a critical bottleneck. State space models, or SSMs, have emerged as a powerful alternative, offering linear time complexity with respect to sequence length while maintaining competitive performance. Grounded in classical control theory, these models map a continuous input sequence to a continuous output sequence through a hidden state space. By combining the training efficiency of parallelizable convolutions with the inference speed of recurrent models, modern SSMs are redefining the frontier of sequence modeling. Let's explore the mathematical foundation that makes this linear time scaling possible. At the core of state space models are continuous time differential equations. An input signal u of t is mapped to an output signal y of t by first projecting the input into an n-dimensional latent state x of t. Mathematically, the derivative of x with respect to t is equal to matrix A times x of t plus matrix B times u of t. The output y of t is then computed as matrix C times x of t. To process digital data, these continuous equations must be discretized using a step size delta. Through bilinear discretization or zero-order hold, the continuous matrices are transformed into discrete matrices A bar and B bar. This allows the model to be computed either recurrently for ultra-fast, constant-time inference, or convolutionally as a single parallel pass during training. While classical SSMs like S4 excel at long-range dependencies, they struggle with content-dependent reasoning tasks because their transition matrices are static and independent of the input tokens. Mamba, introduced by Gu and Dao, addresses this limitation by making the discretization step delta and the projection matrices B and C dynamic functions of the input token at each step. This input-dependent selectivity allows the model to selectively remember or forget information along the sequence. However, dynamic matrices break the convolutional parallelization property. To maintain training efficiency, Mamba leverages a hardware-aware parallel associative scan, streaming intermediate states directly through fast GPU SRAM and avoiding slow off-chip memory writebacks. Building on Mamba-2 introduces structured state-space duality, or SSD, which establishes a formal mathematical connection between selective SSMs and attention mechanisms. SSD shows that selective SSMs can be cast as semi-separable matrices, which compute a form of linear attention where the key value states are decayed over time by the transition matrix. By framing SSMs as dual attention formulations, Mamba-2 enables the use of tensor parallelism and highly optimized matrix multiplication kernels. This dual framework achieves 2 to 8 times faster training and inference throughput compared to Mamba-1, merging the theoretical scaling benefits of state space models with the hardware efficiency of attention. The evolution from standard self-attention to structured state-space duality marks a profound shift in sequence representation. By combining linear time and space complexity with dynamic, content-dependent selectivity, Mamba and Mamba-2 offer a scalable alternative to traditional transformers for long-context applications. To continue exploring the mathematical details and physical hardware co-designs behind modern AI, subscribe to Gemini 3.5 Flash Model. Let's keep optimizing the future of computation.